Most years, you might spot a single bright comet blazing across the sky. But in late 2025, NASA is tracking something unprecedented. 7 giant comets, including the interstellar Rogue 3 I/Atlas, are plunging into the inner solar system within just 6 months. The odds of such a swarm are less than 1 in 2,000, shattering every record since digital surveys began. With names like Swan, Lemon, and Atlas crowding the calendar, astronomers warn this rare convergence could trigger solar storms or produce naked-eye wonders. The skies have never looked like this before. But why are so many cosmic icebergs arriving now? And just how big could the risks or revelations be? 7 major comets racing through the inner solar system in half a year is not just rare, it's a statistical outlier that defies a century's worth of observing logs. Since the dawn of digital sky surveys in the 1990s, the Minor Planet Center's records show an average of 2 or 3 bright comets each year. Even in the busiest seasons, astronomers might catch 4 significant comets passing close enough to study in detail. But 7, all within a single 6-month window, is an event so unlikely that NASA statisticians place the odds at less than 1 in 2,000. That figure isn't just a guess. It's grounded in decades of data and the mathematics of chance. To calculate the probability, researchers turn to the Poisson process, a standard tool for modeling rare, random events. Given the average rate of bright comets, about 2.5 per year, the expected number in any 6-month stretch is just over 1. The chance of 7 arriving in that same period drops to a fraction of a percent. Monte Carlo simulations, running the numbers across hundreds of thousands of hypothetical years, confirm the result. In almost every outcome, the sky stays quiet, with only the occasional outlier. The last time comet counts even approached these numbers, astronomers were still using glass plates, and most discoveries relied on luck or word of mouth. Modern surveys like Pan-STARRS, Atlas, and NEO-WISE have transformed comet hunting. Automated telescopes sweep the sky every night, logging faint objects that would have slipped past earlier generations. Yet even with these powerful tools, the digital era has never delivered a season with more than 4 major comets inside 2 astronomical units of the Sun. That makes 2025 a statistical shock, a year that stands apart from everything astronomers have come to expect. It's not just the total number that's remarkable. The clustering of perihelion dates, with most comets reaching their closest approach between August and December, creates a kind of cosmic traffic jam. Instead of a slow trickle, the inner solar system faces a concentrated rush, each object threading its way past the planets in rapid succession. This kind of convergence is more than a curiosity. It challenges long-held assumptions about the randomness of comet arrivals and the processes that send these icy bodies hurtling sunward. Some researchers are already re-examining the models that predict comet influx rates, wondering if distant gravitational nudges or subtle solar cycles might be at play. Others look to the outer reservoirs, the Oort cloud and the scattered disk, searching for patterns that could explain such a dramatic spike in activity. With the statistical groundwork laid, the next question is clear. Who are these cosmic visitors, and what secrets do they carry as they dive toward the Sun? 7 comets, each with its own schedule and path, are set to sweep through the inner solar system in a rare, tightly packed sequence. The first, C/2022 N2 Pan-STARRS, reaches perihelion on July 31st, 3.83 astronomical units from the Sun, far beyond Mars, where sunlight barely touches its icy surface. Pan-STARRS marks the quiet start, its faint presence a distant signal of what's to come. September brings a dramatic shift. C/2024 P4 Swan, discovered by amateur astronomers using SOHO's Solar Wind Anisotropies instrument, makes its closest approach on September 16th, just 0.50 astronomical units from the Sun. That's inside Mercury's orbit, close enough that Swan could flare into view for the naked eye. Its steep path and rapid approach have already caught the attention of skywatchers, eager for the first visible sign of the swarm. C/2024 R3 Pan-STARRS follows on September 28th at 0.91 astronomical units. Born from the Pan-STARRS survey, it's expected to grow a distinct tail, offering a target for both backyard telescopes and professional observatories tracking solar wind effects. October is the heart of the action. C/2025. J1 Pons Brooks, known for sudden outbursts, reaches perihelion on October 14th at 0.78 astronomical units. Its history of explosive activity, jets of dust and gas erupting from its core, makes it a comet to watch as it threads through the crowded inner system. Then comes the outlier, 3I/Atlas, officially C/2025 N1. This interstellar visitor, on a hyperbolic path, passes the Sun on October 30th at 1.40 astronomical units. Unlike the others, Atlas isn't bound to the Sun. It's a brief guest from beyond, its passage a rare chance for planetary scientists to study an object from another star system. For much of its closest approach, Atlas hides behind the Sun, reappearing in November as it heads back into interstellar space. C/2025. F2 Lemon, discovered by a retired engineer in the UK, reaches perihelion on November 21st at 0.37 astronomical units. Lemon's timing overlaps with Atlas's outbound leg, creating a window when two major comets may share the same patch of sky. Lemon's early discovery has already sparked excitement among amateur observers who hope for a bright tail and possible outbursts. December rounds out the season. C/2024. V2 Hoba arrives. December 4th at 1.32 astronomical units, its arc overlapping Lemon and Atlas. Finally, C/2025. S1 Neowise closes the sequence on December 15th at 1.08 astronomical units, watched for any late surge in brightness. Stacked together, these 7 perihelion dates create a compressed calendar unlike anything in recent memory. With the timing mapped, attention turns to 3I/Atlas, the interstellar wildcard, and what its fleeting visit might reveal. 3. I/Atlas is not just another comet on the 2025 roster. It's the third known interstellar object to cross our solar system, and its chemistry is rewriting the rulebook. Early spectra from the James Webb Space Telescope and the Very Large Telescope revealed a composition that stands apart from both the Oort cloud and previous interstellar visitors. The numbers are startling. Carbon dioxide outweighs water ice by a factor of 8. Carbon dioxide to water measured near 8:1. That's a reversal of the usual order, where water dominates and carbon dioxide is a secondary player. Astronomers have rarely seen such a carbon dioxide-rich body, even among the most distant solar system comets. But the surprises don't end there. As 3I/Atlas approached perihelion, the VLT's X-Shooter spectrograph picked up strong emission from atomic nickel. Distinct, robust nickel won lines in the optical. In ordinary comets, nickel and iron appear together, usually in a balanced ratio. Here, iron is conspicuously absent. Deep exposures aimed at iron 1 lines came up empty despite sensitivity that should have revealed even a trace. The result breaks the expected pattern: a comet rich in nickel, yet seemingly starved of iron. Researchers are now debating whether this points to a unique formation environment or if some unknown process is selectively releasing nickel, perhaps from carbonyl compounds or organics, while iron remains locked away. The coma of Atlas adds another puzzle. Its visible glow is blue-green, a color that usually signals the presence of dicarbon molecules, C2. Yet, the classic C2 band is missing. Instead, the green hue may come from an as-yet unidentified molecule or a rare combination of CN and other fluorescing gases. This oddity has forced a re-examination of how cometary comae form their colors and what chemical pathways might be active in interstellar ices. Other molecules round out the list of oddities. Carbonyl sulfide, a sulfur-bearing gas, was detected in the coma, along with small but significant amounts of carbon monoxide and rising cyanogen emission as the comet closed in on the Sun. The dust grains themselves show strong negative polarization at small phase angles, a signature more typical of trans-Neptunian objects than of garden-variety comets. This hints at a mix of icy and dark, possibly organic-rich grains, preserved from a region far beyond our own solar system's planetary zone. Taken together, These findings have planetary scientists questioning the boundaries between solar system and extrasolar chemistry. If 3I/Atlas shares some molecules with local comets, yet displays ratios and spectral features never seen before, what does that say about the universality of planet formation? Dr. Mira Andrews, principal investigator on the JWST campaign, puts it simply. Atlas shows us that the chemistry of interstellar comets is at least partially cosmic common ground, but it also throws us curveballs we can't yet explain. As the comet heads toward its closest approach, every new dataset becomes a test of old theories, hinting at deeper links between the chemistry of distant star systems and the raw ingredients of our own. Soon, the question will shift. How might these alien materials interact with our sun's magnetic storms, and what new phenomena could unfold as the swarm draws nearer? Tail disconnection is no longer a textbook event from past missions. It's playing out live across the 2025 sky. In mid-September, the LASCO C2 camera aboard SOHO captured the ion tail of C/2024 P4 Swan snapping away within hours of a coronal mass ejection. The severed streamer drifted off as a new one formed in its wake. Just weeks later, C/2024 R3 Pan-STARRS showed the same abrupt break, this time timed almost to the minute with a sector boundary crossing in the interplanetary magnetic field. Ground-based observers scrambled to document the change, while Mars Express relayed images from a different angle, confirming the event was global, not just a trick of perspective. The physics behind these moments is a battleground for competing theories. One camp, led by NASA's Community Coordinated Modeling Center, points to magnetic reconnection as the main culprit. According to their simulations, when a comet's plasma tail meets a sharp flip in the solar magnetic field, a sector crossing, the field lines in the comet's ionosphere are forced to realign. The old tail can't adjust, so it's cut loose, floating away as a new tail grows in the new field direction. Real-time data from Parker Solar Probe and Solar Orbiter back this up. Magnetometers recorded abrupt polarity reversals within hours of each observed tail break, and solar wind speeds spiked to over 550 kilometers per second. But the story isn't settled. Dr. Kara Simmons, Parker Solar Probe team lead, warns that not every tail break fits the classic script. In several cases, especially during the October 17th event on C/2025 D1, the break happened without a clear magnetic reversal. Instead, a sudden pulse of high-speed solar wind arrived, ramping up pressure and stripping away the ion tail by brute force. Laboratory plasma experiments hint at another possibility. Electrostatic fields generated by differential ion flows can split a tail even in steady magnetic conditions. Simmons and her colleagues argue that the swarm is revealing a more complex picture, sometimes reconnection, sometimes dynamic pressure, and sometimes a blend of both. This debate is more than academic. NASA's modeling teams are using every tail break as a real-world test for their space weather forecasts. If a comet's passage can amplify or modulate solar outbursts, the implications reach far beyond astronomy, touching everything from satellite safety to radio blackout risk. The 2025 swarm, with its parade of live disconnection events, is forcing agencies to rethink operational protocols and revisit the limits of their predictive models. As the season continues, each comet becomes both a messenger and a stress test for the science of solar-comet interactions. Discovery, in 2025, was not just the domain of high-powered observatories. The first alerts came from a global relay of eyes and algorithms, some professional, many not. On July 1st, the Atlas team in Chile logged an object with a trajectory that did not fit any solar system pattern. Within hours, their software flagged it as a possible interstellar visitor. The team's lead, a quiet data analyst known for marathon coding sessions, sent out the first circular. The excitement was immediate. In Australia, Greg M., a school teacher by day and comet hunter by night, had already been poring over SOHO's SWAN data. He caught a sudden brightening, cross-checked the coordinates, and realized he was looking at a new inbound comet. Greg's discovery, C/2025 R2 SWAN, spread quickly through amateur networks. His friends started a crowdfunding campaign for a better telescope, and within days, backyard observers across 3 continents were reporting in. Across the Atlantic, a retired engineer in the UK wrestled with a bulky telescope mount and cloudy skies. He almost missed the narrow window, but a single clear night in March let him spot a faint smudge. Careful reporting and help from an online forum led to confirmation. C/2025 F2 Lemon. The engineer's name joined the official designation, a nod to persistence and the power of citizen science. These stories, repeated in forums and group chats from India to Indiana, turned discovery into a communal event. Each new comet sparked a wave of excitement, drawing in veteran skywatchers and newcomers alike. The relay of observations, data passed from hand to hand, time zone to time zone, built a living map of the swarm's progress. In 2025, discovery was not a solitary act, but a chorus, echoing across the globe as the comets closed in. NASA's operations room, usually a place of routine cadence, became a hive of tactical adjustments as the comet swarm advanced. Deep Space Network operators, already juggling a packed schedule, faced a new kind of congestion, one driven not by human missions, but by the unpredictable effects of comet tails and solar activity on radio transmissions. Internal memos circulated among DSN teams, flagging windows of heightened plasma turbulence as several comets threaded their ion tails across the Sun. Probe line of sight. The risk wasn't hypothetical. Simulations projected brief but real chances of radio blackouts for Mars Express and Solar Orbiter, especially during September and October, when Swan and Lemon made their closest solar passes. For the first time, mission planners recommended contingency slews, rotating high-gain antennas away from the Sun for hours at a time and pausing ultra-sensitive science measurements during peak risk intervals. These operational shifts rippled outward. NASA's Public Affairs Office coordinated with observatories and citizen science networks, releasing updated visibility forecasts as magnitude predictions sharpened. Several comets, Swan, Lemon, and even 3I/Atlas on its outbound leg, were projected to reach magnitude +4 or brighter, a threshold for naked eye spotting under dark skies. Social media lit up with sky charts and finder guides, while amateur astronomers organized live streams and local viewing parties. Safety bulletins advised caution for solar observers, noting the increased risk of glare and unpredictable outbursts near perihelion. The message was clear. This was not just a spectacle for professionals or backyard astronomers. With the right timing and a clear horizon, millions could witness at least one member of the swarm without optical aid. NASA's response, balancing probe safety with public engagement, turned a rare astronomical event into a shared global experience, inviting anyone with curiosity to look up and join the watch. In 2025, 7 major comets, more than any recorded in the digital era, entered the inner solar system within just 6 months. Observatories confirmed that 3I/Atlas, with its rare carbon dioxide-rich chemistry and hyperbolic orbit, stands apart from known solar system comets. NASA and international teams documented multiple tail disconnection events, linking them to solar storms, but the exact mechanisms remain under active investigation. While Deep Space Network protocols were adapted and 2 comets reached naked eye brightness, the long-term effects of such a swarm on solar activity are still debated in the scientific community. Some data and operational details remain classified, leaving open questions about the broader risks and patterns of comet-sun interactions. What is certain? The 2025 comet swarm has redefined the statistical boundaries of solar system dynamics and given astronomers a rare, real-time laboratory. As researchers analyze petabytes of new data, the mysteries of comets and their role in our cosmic neighborhood remain far from settled.